What no one told you about what is really happening with 3I Atlas. From the very first moment this object crossed the invisible boundary that separates interstellar space from the domain of the Sun, astronomers understood that they were not facing an ordinary traveler. Its trajectory does not match anything produced within our system. Its speed easily exceeds that of any known comet, and its recent behavior has raised questions that no one imagined having to face so soon. Every record obtained reveals details that not only confirm its external origin, but also expose abrupt changes in its activity, variations in its brightness, and emissions that have forced scientists to review data more than once to rule out instrumental errors. The most unsettling aspect is that the more it is observed, the more a scientific coherence emerges that confirms the object is reacting to the Sun in a way different from any previously studied body. The observations show rapid ejections, microscopic fragments detaching at irregular rates, and a green emission pattern that, although it has a chemical basis, appears at uncommon intensities. Each telescope tracking it adds another piece to the puzzle. And yet, the overall picture still does not become completely clear. What no one told you is that its passage is revealing crucial data about ancient regions of our galaxy, because its material preserves the imprint of an environment formed far earlier than the Sun itself. None of this is speculation. These are data confirmed by spectroscopy, photometric analysis, and continuous monitoring from different observatories. And although its path continues moving away after perihelion, its behavior still keeps the scientific community watching every change, because each day brings something new and completely real. Before we continue exploring the interstellar origin and surprising behavior of 3I Atlas, there are 3 quick things you need to do right now to help this information reach more people. First, hit the like button so this video reaches thousands of others passionate about astronomy. Second, subscribe and turn on notifications to stay up to date with every new discovery about 3I Atlas. And third, if this type of deep space content interests you and you want to see more videos like this, drop a 1 in the comments right now. That simple 1 tells the algorithm to show this to everyone else who loves real astronomy. Now let's continue. 3I Atlas is not an ordinary comet, it is not an object repeating a cycle, nor a remnant from our own Oort cloud. Its interstellar nature is confirmed by the exact shape of its orbit, a hyperbolic trajectory that indicates it will not return and that it does not belong to any gravitational component of the Sun. This green visitor arrived from a region far older than any structure in the planetary system, carrying materials that preserve information from deep space. In recent weeks, multiple observatories have recorded relevant changes in its activity, among them variations in gas emission and the presence of ejections that do not follow a regular pattern. These events are not interpreted as fictional anomalies, but as real chemical responses to solar radiation, especially now that its distance from the Sun has changed after perihelion. Images obtained by ground-based and space-based instruments show a clear evolution in its structure, revealing features that allow the study of physical processes that cannot be observed in native comets. Throughout this video we are going to explore in a completely scientific way what has been discovered and what these data mean for better understanding the material that exists between the stars. The information is real, confirmed, and based on verified observations. The interstellar origin of 3I Atlas was established from the very first orbital calculations carried out at the time of its discovery when an object enters the solar system. The shape of its trajectory is the main indicator for knowing whether or not it belongs to this cosmic neighborhood. In the case of 3I Atlas, the eccentricity of its orbit immediately exceeded the value of 1, which means it is not gravitationally bound to the Sun. A body with eccentricity greater than 1 follows a hyperbolic orbit, and that is the exact mathematical signature of an object coming from interstellar space. There are no known mechanisms within the solar system capable of accelerating a comet to this type of trajectory without the help of an additional force. Thus, the evidence showed that its origin lies beyond any region that our planetary system could have generated or influenced. After the discovery, observatories began recording precise positions of the object night after night to refine the orbital parameters. Each independent measurement agreed. Its speed and direction were not compatible with a native body. An object born within our system always maintains some relationship with the ecliptic plane or with the gravitational influences accumulated since its formation. 3I Atlas showed none of these characteristics. Its inclination, its angle of approach, and the velocity vector with which it entered demonstrated that it came from a completely foreign region. Its arrival was neither casual nor the product of a recent interaction. It had been traveling through the interstellar medium for millions of years before crossing into the gravitational reach of the Sun. The first observations also revealed something that further reinforced its external nature. Its entry speed was higher than the solar escape velocity at the distance where it was detected. This means that even before feeling the influence of the Sun, it was already moving too fast to be captured. A local comet, although it can accelerate due to gravitational perturbations, does not spontaneously reach these speeds. For this reason, this datum was one of the most definitive and least debated in the scientific community. Its trajectory simply did not match any known comet family or any cloud of remnants within the system. As the data accumulated, another key element began to emerge: the analysis of the object's motion backward in time. When astronomers traced its orbit backward through numerical simulations, they found no connection with nearby stars or past trajectories within the solar system. The calculations showed that it came from a direction far from the most crowded stellar planes, a region where stars are so distant from one another that they can eject objects into the interstellar void as a result of interactions that occurred billions of years ago. This supports the idea that its origin lies in a planetary system that no longer has any influence over it. Another fundamental aspect was the consistency across different observation methods. The position of the object measured both optically and in infrared confirmed the same displacement pattern. There were no divergences or erratic behaviors. Everything followed a physical model consistent with an interstellar object moving under the combination of solar gravity and its own original momentum. Unlike local comets that can be influenced by resonances or planetary perturbations, 3I Atlas crossed the system as a temporary visitor, without staying longer than necessary. Its passage does not respond to cycles or repetitions, but to a single visit driven by its ancestral trajectory. As it approached the Sun, spectroscopic observations began to show signals of the materials that compose it. Although these signals did not yet reveal the full complexity of the object, they did show a pattern compatible with bodies formed in regions external to young systems like ours. Local comets contain known proportions of certain elements resulting from the thermal history of the solar system. 3I Atlas showed variations in these proportions that matched the extreme conditions of interstellar space. These differences fit with a body formed in a distant environment, where interstellar radiation, time, and the absence of a nearby sun modify the material in a way different from any native comet. The confirmation of the interstellar origin was also strengthened by the analysis of the object's color. Although the observed greenish tone has known chemical bases, the measured intensities did not match average values of local comets. This pattern does not contradict any known physics. It simply reflects a distinct composition and thermal history, probably shaped by a cold and dark environment for an immeasurably long period. This added coherence to the idea that the object did not share a common origin with the icy remnants of the Oort cloud. Ground-based stations began to record variations in its brightness throughout its approach. These variations followed a behavior compatible with the sublimation of materials that had never before been exposed to the solar environment. When an interstellar comet enters a young planetary system, the changes can be more abrupt, not because they are anomalous, but because the materials respond more intensely to sudden heating. This provided an additional component of evidence. The object reacted as expected for an interstellar visitor that had never before been close to a star like the Sun. As the data consolidated, it became clear that its origin did not require extraordinary assumptions. All the evidence was consistent with known celestial physics. Its hyperbolic trajectory, its speed, its inclination, the direction of entry, and its response to solar heating formed a solid set of data that ruled out any local origin. In fact, the object fit perfectly into the expected profile of fragments released from distant planetary systems that, after gravitational interactions, end up traveling through the interstellar void for millions or billions of kilometers, even after its perihelion passage. Upon reanalyzing the data, nothing in its behavior contradicts its classification as the third confirmed interstellar object. Its exit from the solar system follows the same pattern of physical consistency it showed from its entry. Thus, the first undeniable scientific conclusion is that 3I Atlas is a messenger from ancient and distant regions of the galaxy, a fragment that preserves information from the environment in which it formed, bringing with it a unique opportunity to study material that was never exposed to our Sun. The composition of 3I Atlas became one of the most studied points since the object entered the region where spectra could be obtained with better resolution. Every comet, whether local or interstellar, reveals its history through the elements and molecules it releases when heated. In the case of 3I Atlas, spectroscopic analyses showed features that drew attention from the start, not because they represented anything impossible, but because they displayed proportions different from those of native solar system comets. One of the first clear signs was the prominent presence of emissions associated with diatomic carbon, responsible for the green glow observed in many comets. But in this object, the measured intensity exceeded common values, which matched the idea that the material had been subjected to extremely cold conditions for long periods before approaching the Sun. When an interstellar comet approaches a star after millions of years in complete darkness, sublimation can release compounds that in local comets would already have been altered by previous solar visits. In 3I Atlas, the spectra revealed chemical signatures indicating the presence of relatively pristine materials, that is, compounds that have not undergone repeated cycles of heating and cooling. This includes simple organic molecules and particular proportions of cyanogen, a compound common in comets, but which in this case appeared in quantities that astronomers are analyzing in detail to compare with other interstellar visitors such as 2I Borisov. The consistency among these values reinforces the idea that interstellar objects can share similar formation processes in deep regions of the galaxy. As the object continued its approach, surface activity began to change, releasing dust and gases that allowed more detailed analysis. The green emission observed at different wavelengths is not a mysterious phenomenon. It is the signal of diatomic carbon excited by solar radiation. What focused the studies more was the way the intensity fluctuated, showing rapid and detectable variations between observation sessions only hours apart. These variations indicated that heating was releasing material irregularly, something consistent with a nucleus composed of sectors with different densities and levels of compaction. A trait expected for an object formed in interstellar environments where aggregation processes can occur less uniformly. Another determining aspect was the direct comparison with 2I Borisov, the other precisely observed interstellar comet. In the case of Borisov, the proportions of carbon monoxide were notably higher than in most solar system comets. In 3I Atlas, although the data are still under analysis at several observatories, the initial measurements also point to the presence of volatile compounds at levels suggesting a colder origin than the average for local comets. This does not contradict what was observed in other interstellar visitors and strengthens the scientific interpretation that comets from outside the solar system preserve different abundances of frozen gases. Dust observations also provided important elements. When activity increased near perihelion, the tail showed particles with varied reflectances, indicating a complex mixture of minerals. Local comets usually show more homogeneous patterns due to the shared thermal history within the solar system. 3I Atlas, in contrast, exhibited a combination of grains with different sizes and optical properties, something consistent with a nucleus formed in a distant system where planetary formation processes follow different rhythms and produce different mixtures of materials. This allows researchers to study not only the composition of the object, but also to compare it with models of planetary formation in external systems. Spectral analysis also showed lines associated with sublimated water, one of the fundamental components of comets. However, the ratio between water vapor and other volatile gases indicated that the object was releasing materials that had remained protected in deep layers of the nucleus for long periods. This is consistent with an interstellar visitor, since objects of this type can preserve their original material without significant alterations due to the enormous amount of time they spend far from any star. The low interaction with external heat sources preserves compounds that in local comets would already have been modified after multiple solar approaches. Another relevant finding was the detection of changes in the sublimation rate after perihelion. As it began to move away, activity did not decrease as quickly as it does with many native comets. This difference is not interpreted as anomalous behavior, but as a reflection of the internal composition. When an interstellar comet is heated for the first time, its nucleus can contain deep reserves of volatile materials that take longer to sublimate completely, prolonging the period of activity even when the distance to the Sun is already increasing. This phenomenon was also partially observed in 2I Borisov, adding consistency among the data. Comparison with solar system comets remains a central piece of the research. Astronomers use these contrasts to understand differences in the environments where they form. 3I Atlas appears to contain particular proportions of certain compounds suggesting an origin in a colder system, possibly located at the periphery of a distant star where chemical processes advance at extremely slow rates. This does not contradict any existing theory and instead enriches the models that try to explain how icy bodies form and evolve in different regions of the galaxy. Throughout its observations, several instruments detected a stable pattern. The spectral emissions were consistent with a comet composed of ancient materials that had not experienced complex thermal cycles. This makes its study especially valuable for astronomy, as it offers a unique opportunity to analyze material that represents the chemical infancy of distant regions. Each spectrum obtained with the object reveals details that allow reconstruction of the environment where it formed, a place that probably had extremely low temperatures and a very different radiation level from that near young stars like the Sun. Finally, the presence of the green tone, although it attracts public attention, is completely understandable from science. It is related to the photodissociation process of diatomic carbon, a well-documented phenomenon in active comets. What distinguishes 3I Atlas is the intensity with which it presents itself, which matches its composition rich in carbon compounds. This adds another layer of useful information for characterizing its internal structure and the type of materials it contains. The ongoing analysis of its composition is helping to understand not only the object itself, but also the processes that occur in planetary formation regions outside the solar system. Each measurement adds one more piece to the chemical puzzle, allowing comparison of the data with theoretical models that describe how compounds are distributed in protoplanetary disks of distant stars. This turns 3I Atlas into an exceptional source of scientific information. The activity recorded in 3I Atlas since its arrival in the solar system has been one of the most analyzed areas by astronomers, not because it presents behaviors outside known physics, but because it allows direct observation of how an interstellar object reacts when it encounters solar radiation for the first time. Every comet responds in a particular way to heating, depending on its internal structure, the distribution of its materials, and the amount of volatile compounds trapped in its nucleus. In the case of 3I Atlas, the first measurements on its light curve began to show a pattern that caught attention: rapid and pronounced variations in brightness, indicating that the object was experiencing irregular sublimation processes as it moved toward warmer regions of the system. Photometric monitoring revealed that the activity rate changed over relatively short time intervals, suggesting that the nucleus contained zones with different levels of cohesion and density. This heterogeneous structure is completely consistent with an object formed in an interstellar environment where aggregation processes can be slow and not always uniform. In these cases, solar heating can cause specific sectors of the nucleus to release gases and particles more intensely, generating perceptible variations in brightness within hours or days. These observations do not imply anomalous behaviors, but rather reflect a composition that has not been processed by repeated thermal cycles, as occurs in native solar system comets. Images obtained by telescopes equipped with cameras capable of detecting structural changes in the coma showed that the object developed ejection patterns that varied in direction as it rotated on its axis. This rotational movement exposes different regions of the nucleus to heat, and each can respond differently. In the case of 3I Atlas, some areas showed stronger activity, releasing jets of dust and gas known as jets. These jets, observed in numerous comets, allow study of the internal distribution of material and are important tools for inferring the structure of the nucleus. The presence of jets in 3I Atlas revealed nothing outside known science. It simply confirmed that the object contained sectors rich in volatile compounds that reacted to sudden heating. One of the most interesting elements was the appearance of variations in the morphology of the tail, visible in images obtained with specific filters. A comet's tail forms through the interaction between released particles and the solar wind that pushes the material in a direction opposite to the Sun. In the case of 3I Atlas, adjustments in the shape of the tail were observed that coincided with changes in the internal activity of the object. These adjustments were neither abrupt nor contradictory. Rather, they reflect natural responses to the combination of nucleus rotation, dust release, and solar wind pressure. Each observed modification added more information about the rate of material release and the size of expelled particles during activity. As the object approached closer to the Sun, it began to show a significant increase in the sublimation rate. This is completely expected for any comet, but in 3I Atlas it had particular characteristics because its compounds were being heated for the first time in millions of years. The sublimation process of the most volatile materials is usually more intense in interstellar comets, since these compounds remain intact for long periods without exposure to stellar radiation. Therefore, their release can generate abrupt increases in brightness and more powerful activity episodes. These events were recorded and analyzed in detail, showing behavior completely coherent with physical models of comets experiencing their first encounter with a warm environment. Spectral analysis allowed identification of specific moments when the object expelled more particles, coinciding with detected changes in luminosity. These activity peaks also provided a window to study the emission of certain compounds. When sublimation increases, molecules excited by solar radiation produce bright lines in the spectrum, allowing precise identification of what the object is releasing. In the case of 3I Atlas, these emissions confirmed the presence of typical comet compounds such as cyanogen, water, and carbon-rich dust particles, but distributed in a way that suggests an origin in an extremely cold and distant environment. Another observed phenomenon was the appearance of microscopic fragments that detached from the object during periods of more intense activity. These fragments do not represent catastrophic ruptures of the nucleus, but normal releases of particles adhered to the surface or located in internal cavities. Their detection was possible thanks to high-resolution observations that revealed irregular dust concentrations near the coma. In interstellar comets, where cohesion between materials can vary due to lack of prior exposure to heating, this type of detachment is especially common. Each analyzed fragment provides information about the texture of the nucleus and how the material was assembled in its region of origin. Images obtained after perihelion also showed a change in the object's behavior. Although the distance to the Sun began to increase, activity continued for a more prolonged time than observed in many native comets. This is due to the deepest layers of the nucleus still containing volatile compounds that were in the process of sublimation. The object's thermal inertia, combined with the presence of unprocessed materials, allowed activity to persist even when solar heat was no longer as intense as at the closest point to the Sun. This continuity contributed to generating valuable data for studying how interstellar comets evolve after passing through their first perihelion. The recorded activity also allowed astronomers to analyze the object's rotation with greater precision. By observing the direction and intensity of jets at different moments, it was possible to estimate the spin rate of the nucleus. These data are essential for understanding the object's stability and for identifying whether rotation may have influenced material release. In the case of 3I Atlas, the estimated rotation showed no signs of instability, suggesting that the nucleus has sufficient internal cohesion to withstand activity without significant fragmentation. The study of 3I Atlas activity continues to provide important information for understanding interstellar objects. Every change in its brightness, every variation in the tail, and every detected emission contribute to reconstructing the internal structure of the object and inferring the conditions of the environment where it formed. These data, added to composition analyses, allow construction of a complete picture of this interstellar visitor, a body that preserves in its nucleus the chemical history of a distant region of the galaxy. The passage of 3I Atlas through perihelion represented one of the most important moments for its study, because it allowed real-time observation of how an interstellar object reacts to the maximum level of solar radiation it will encounter throughout its trajectory through the system. Perihelion marks the closest point to the Sun and therefore the moment when changes in activity, surface temperature, and material release reach their most critical point. In the case of 3I Atlas, every observatory tracking it knew that this phase would offer unique data, not only on the intensity of its activity, but also on the internal structure of the body and its ability to withstand thermal stress. Measurements taken during its approach showed a progressive increase in the sublimation rate. This is completely coherent with the behavior of any comet, but in interstellar objects it usually acquires particular nuances due to the pristine composition they preserve. 3I Atlas had been millions of years without direct exposure to a star. Therefore, the abrupt heating caused a rapid release of volatiles trapped in internal cavities. The immediate consequence was a notable increase in brightness accompanied by expansion of the coma, which became denser and more extensive as solar radiation penetrated deeper layers of the nucleus. Spectroscopic observations obtained at perihelion showed an intense concentration of molecules excited by radiation. Among the most prominent were clear signals of water vapor, cyanogen, and diatomic carbon. The increase in diatomic carbon emission reinforced the green coloration that numerous observatories recorded clearly. This glow is neither strange nor indicates any exotic phenomenon. It responds to a well-documented chemical process. What drew attention was the stability of the phenomenon with an intensity that remained for several hours around perihelion, suggesting that internal layers of the nucleus were releasing fresh compounds as heat distributed. The tail structure also showed relevant changes. Interaction with the solar wind intensified, allowing study of the size and speed of released particles. As the object approached the Sun, the tail extended further and adopted a slightly curved pattern, the result of the combination of solar wind pressure and comet rotation. This behavior is completely expected, especially in comets with high activity levels. Variations in tail morphology during perihelion allowed identification of nucleus regions releasing material more intensely, coinciding with the irregular distribution of volatile compounds observed in other phases of its approach. Perihelion also allowed evaluation of the nucleus resistance to fragmentation. Many comets experience partial ruptures or more noticeable detachments when exposed to extreme solar heat, especially if their internal structure is fragile. In the case of 3I Atlas, data collected during this period showed no evidence of significant nucleus rupture, although microscopic fragments and local variations in coma intensity were detected. Nothing indicated major disintegration. This suggests that the object's nucleus has sufficient internal cohesion to withstand thermal stress without catastrophic fragmentation, at least during this phase. Something especially relevant was the temporary appearance of an anti-coma, an optical structure produced by particles moving in a different direction from the main tail due to their size and the perspective from Earth. This phenomenon, though uncommon, has well-known physical foundations. The anti-coma does not indicate strange behavior, but reveals details about particle distribution in space near the comet. Images obtained showed that larger particles moved in a slightly different direction from smaller ones, fitting with dust analysis performed in other phases of the object's study. During perihelion, activity peaks were recorded that coincided with periods when the object's rotation exposed particularly volatile zones of the nucleus. These episodes were detected in photometric measurements that showed temporary brightness increases. Each peak represented an opportunity to analyze emission composition, and several observatories took advantage of these moments to obtain high-resolution spectra. The combination of these data allowed comparison of the object's chemical signatures with those of other interstellar visitors, finding similarities that reinforce coherence between both bodies. As the object crossed the closest point to the Sun and began its departure, instruments continued recording changes in its activity. Although radiation intensity decreased gradually, the nucleus thermal inertia maintained sublimation processes for a time. This produced a smooth transition in which activity reduced but not immediately. This continuity reflected that heat had penetrated deeper, releasing materials previously unexposed. This post-perihelion phase is particularly important because it allows evaluation of the comet's internal structure and study of how primitive material responds to prolonged thermal changes. Post-perihelion photometric analysis also showed variations in the object's rotation. Asymmetric activity can slightly modify spin rate due to thrust reactions generated by jets. These changes, though minimal, provide key information about material distribution and nucleus stability. In the case of 3I Atlas, obtained values showed no dangerous variations or signs of spin-up that significantly affected its integrity. This confirmed that despite extreme heating, the object maintained a relatively stable structure. Data obtained at perihelion are essential not only for understanding 3I Atlas, but also for comparing it with other interstellar visitors. Every external comet crossing the solar system provides information about chemistry and physics of regions we cannot study directly. The behavior of 3I Atlas in this phase matches what has been observed in other interstellar origin bodies monitored with modern instruments. The coherence among these data reinforces the reliability of conclusions and contributes to the study of formation processes in older and more distant planetary systems. Finally, the perihelion passage allowed establishment of a complete profile of its thermal behavior. The collected dataset shows an object that responds naturally to solar heating with intense but consistent activity, release of primitive compounds, and an internal structure capable of withstanding the most demanding phase of its journey through the solar system. Scientific images obtained of 3I Atlas after perihelion became one of the most valuable elements for understanding the object's immediate evolution after facing its point of greatest heating. These images, taken from ground-based and space-based telescopes, not only recorded the comet's general appearance, but also allowed precise analysis of the coma structure, dust distribution, and tail changes during the hours and days following the close encounter with the Sun. Each visual record became a fundamental piece for mapping the object's response to extreme heat and for understanding what materials were being released as the nucleus continued sublimating. One of the first observed points was the temporary expansion of the coma. After perihelion, the cloud of gas and dust around the comet became more extensive, indicating that heat absorbed during its close passage continued releasing compounds trapped in deeper regions of the nucleus. This expansion did not occur abruptly, but developed in a progressive pattern consistent with the object's gradual cooling. High-resolution images showed differences in coma density depending on the observation angle, allowing researchers to identify areas where sublimation continued with greater intensity. This behavior is typical of objects experiencing their first encounter with a star, since the internal structure still preserves highly volatile materials that had not been previously exposed. The images also captured changes in the tail appearance. In the days following perihelion, the 3I Atlas tail showed variations coinciding with the gradual decrease in nucleus activity. Smaller particles, strongly influenced by solar radiation, began to disperse faster, generating a thinner and more extended tail. Meanwhile, larger particles maintained a more stable trajectory, contributing to the formation of visible structures that allowed estimation of the size and distribution of released dust. Photometric analyses derived from these images confirmed a gradual transition in tail composition with a predominance of fine particles during the first days and a progressive reduction as the comet moved away from the Sun. In some images, especially those taken with specific filters, it was possible to observe regions where dust appeared to organize into more defined patterns. These patterns are effects generated by the combination of nucleus rotation and dust dispersion in different directions. The presence of curved structures and divergent segments in the tail is a well-documented behavior in comets with elevated activity. And in the case of 3I Atlas, this phenomenon fit with the estimation that the object maintained a constant rate of material release for several days. There were no signs indicating anomalous behaviors or important structural ruptures, which reinforced the interpretation of a nucleus that, although exposed for the first time to a star, preserved sufficient internal cohesion. Another highlighted aspect was the detection of regions with reduced brightness within the coma, areas that appeared slightly less illuminated compared to the rest of the cloud. This effect does not imply absence of material, but differences in local dust density or variations in the amount of emitted gas. In comet observations, these contrasts are useful indicators for analyzing coma texture and for identifying possible zones in the nucleus with irregular activity. In 3I Atlas, these zones were interpreted as the result of the object's heterogeneous structure, where different nucleus layers responded to heat differently. The images confirmed that even after perihelion, the object maintained an active but stable pattern. Images captured by more sensitive telescopes allowed observation of minor details such as the presence of small dust arcs that temporarily detached from the coma. These arcs, which form when particles are impulsed by specific nucleus jets, are common in comets with asymmetric activity. Their presence in 3I Atlas provided additional information about jet direction and material release rate. The distribution of these arcs also allowed inference of internal cavities where volatile compounds were stored, a trait consistent with an interstellar object that had never before experienced the thermal pressure of a nearby star. After perihelion, the images continued revealing characteristic features of the object's interaction with the solar wind. Slight separations were detected between different particle streams within the tail, a phenomenon produced when solar wind intensity changes or when particles exhibit variations in size or electric charge. These phenomena were interpreted as evidence of the dynamic environment around the comet and allowed calculation of the speed at which particles were expelled. In the case of 3I Atlas, obtained values coincided with activity observed in highly active comets and were completely coherent with physical models describing dust behavior under solar influence. Post-perihelion images also allowed observation of the overall color evolution of the object. Although the coma continued showing a greenish tone due to persistent diatomic carbon emission, this color began to decrease gradually as nucleus activity reduced the release of related compounds. This decrease in color intensity is a natural indicator that the proportion of excited molecules in the coma was declining, coinciding with the predicted reduction in sublimation activity as the object moved away from the Sun. The color behavior in these images was one of the most studied aspects because it allowed tracing the comet's activity curve in a visual and direct way. Another important element revealed by the images was the confirmation that nucleus integrity remained stable. There were no indications in the images of large fractures or divisions, something that occurs in some comets when their internal structure cannot withstand perihelion thermal pressure. In 3I Atlas, the absence of these fractures showed that its internal cohesion was adequate to withstand the phase of greatest thermal stress. This does not mean that microscopic fragments were not detached as these were observed in the coma, but their presence is an expected behavior and does not imply major nucleus rupture. Post-perihelion images also helped calibrate numerical models on dust dispersion. By comparing sequences taken on different days, astronomers were able to measure the speed at which the coma expanded and the tail stretched. These data are essential for estimating the amount of material released during different activity phases of the object. In the case of 3I Atlas, The models coincided with the interpretation that the comet maintained a relatively high level of activity in the days following perihelion due to continuous release of internal compounds. Finally, all these images allowed construction of a detailed record of the object's behavior after its encounter with the Sun. The coherence between the obtained data and existing theories on the behavior of interstellar comets reinforces the scientific importance of 3I Atlas as a unique opportunity to study primitive materials that have traveled through deep space for millions of years. The role of the James Webb Space Telescope and other advanced instruments was essential for understanding 3I Atlas in greater depth after its entry into the solar system. Although ground-based observations provided an enormous amount of valuable information, space-based instruments allowed analysis of details impossible to detect from the surface. The absence of atmospheric distortions, the extreme sensitivity of their detectors, and the ability to capture wavelengths invisible from Earth turned the Webb, the Hubble, and other observatories into key pieces for studying the composition, structure, and thermal evolution of the object. The James Webb Space Telescope, with its ability to operate in infrared, played a fundamental role because this range is ideal for identifying compounds released when a comet experiences solar heating. Spectra obtained by its instruments allow detection of specific molecules through their thermal signatures, even when present in very small quantities. In the case of 3I Atlas, infrared observations confirmed the presence of carbon compounds, sublimated water, and other volatiles evaporating from internal layers of the nucleus. The Webb sensitivity allowed differentiation between regions where material was being actively released and more stable zones where sublimation was lower, in addition to identifying compounds. The Webb also allowed study of the object's thermal distribution. By analyzing how certain materials emit infrared radiation as they heat up, it is possible to estimate the average nucleus temperature and its evolution during perihelion. In 3I Atlas, these measurements showed a pattern consistent with an interstellar body where the deepest layers retained cold longer due to their natural thermal insulation. This thermal inertia explains the prolonged activity observed after perihelion, as heat slowly penetrated those internal layers, releasing compounds that had been protected for millions of years. Another crucial instrument was the Hubble Space Telescope, which contributed high-resolution images in the optical spectrum. Although Hubble cannot capture chemical details as deep as the Webb, it does have the ability to record extremely fine changes in the structure of the coma and tail. Hubble images allowed identification of small asymmetries in dust release, providing clues about possible active zones in the nucleus. The stability of Hubble observations also allowed comparison of changes between consecutive days, creating a detailed visual record of the object's dynamic behavior. The combined data from both telescopes showed that 3I Atlas had activity that varied as it rotated, implying that different areas of the nucleus presented different levels of compaction, density, and volatile content. These differences are common in comets, but in an interstellar object they are especially valuable because they reflect the conditions of the place where it formed. The obtained information suggests that the original environment of 3I Atlas had extremely low temperatures, probably in the peripheries of a distant planetary system where stellar radiation was minimal and allowed preservation of primitive compounds. Another important observatory was the future Vera C. Rubin telescope, which, although not yet performing complete observations in all its capacities, is already being used for preliminary studies of fast-moving objects. The Rubin is especially relevant because its design allows capture of wide-field images with high frequency, facilitating continuous monitoring of objects in motion like 3I Atlas. Although its data do not have the same detail as those from the Webb or Hubble, they do allow recording of visible changes in reflected light and general comet activity on short time scales. These changes help build light curves that allow estimation of nucleus rotation and surface activity variability. Pan-stars, which played an important role in detecting several interstellar objects, also contributed to the study of 3I Atlas through high-precision photometric measurements. Its ability to detect minimal brightness variations allowed tracing a detailed map of how comet activity changed during its passage through the inner regions of the solar system. These measurements complemented data from space telescopes, providing context on how activity evolved at different solar distances. In addition to these instruments, several ground-based observatories equipped with advanced spectrographs contributed essential data. Each spectrum obtained from Earth allowed comparison of Webb infrared measurements with signals detected in visible and ultraviolet. This allowed astronomers to study how certain molecules behaved at different energy ranges, which is fundamental for reconstructing the object's chemical structure. In particular, the presence of diatomic carbon that generates the characteristic green emission was carefully analyzed through these spectrographs, confirming that its intensity fluctuated as solar radiation heated specific nucleus layers. The use of multiple telescopes allowed creation of a complete picture of 3I Atlas behavior. For example, while the Webb detected compounds hidden in infrared, Hubble documented the visual evolution of the object. Pan-STARRS developed its light curve, and several ground-based telescopes complemented with chemical analyses. This combination of perspectives allowed obtaining extremely detailed information that would not be possible with a single instrument. International collaboration was another key aspect during this process. The study of interstellar objects requires coordination among teams from different countries to ensure the object is monitored continuously. Since 3I Atlas activity varied within hours, having observatories distributed around the world allowed recording every change without losing significant information. This ensured constant coverage during the most critical phases such as perihelion and the following days. The role of the Webb deserves special emphasis due to its unprecedented ability to study the object's chemistry. Each obtained spectrum represents a direct window into the comet's history. The Webb not only detected typical comet volatile compounds, but also allowed study of the molecular structure of expelled material. This helps scientists understand how interstellar materials can influence the evolution of planetary systems by being transported from one star to another over millions of years. Finally, the combined information from all these instruments has allowed construction of a clear and coherent image of 3I Atlas as an active interstellar comet composed of primitive materials and with behavior completely consistent with expected physics. Each observatory contributed a unique piece of the puzzle, and together they created the most detailed record obtained so far of an interstellar visitor passing through the solar system. The changes recorded in the nucleus and tail of 3I Atlas after its perihelion passage became one of the most important keys to understanding its internal structure and how an interstellar object responds to stellar heat for the first time in millions of years. Every comet, regardless of origin, undergoes transformations when approaching the Sun. But in interstellar comets these transformations can be even more revealing because their material is in a more primitive state. 3I Atlas offered an exceptional opportunity to study these processes, as it showed clear, consistent and scientifically valuable activity patterns. One of the first elements analyzed was the brightness variation of the nucleus. Photometric measurements showed fluctuations directly associated with material release from specific nucleus sectors. This indicates that the object has a heterogeneous surface where some regions contain volatile compounds in greater proportion than others. This type of structure is common in comets, but in 3I Atlas it is especially relevant because the internal differences reflect the environment in which it formed. In interstellar environments, where aggregation and consolidation processes occur under extremely cold conditions without the presence of a nearby star, nuclei can acquire textures and material mixtures distinct from those observed in the solar system. Spectroscopic data also showed evidence of chemical variations in different zones of the nucleus. During phases of greatest activity, increases were detected in emissions of molecules such as cyanogen and diatomic carbon. These fluctuations do not indicate anything unusual, but are normal signals of nucleus sectors where volatiles sublimate more rapidly. As the object rotated on its axis, telescopes detected changes in the intensity of these emissions, demonstrating that nucleus rotation exposes different areas to solar heat at regular intervals. This rotation also influences how the tail forms and evolves since particle release is not uniform in all directions. The observation of jets was another significant feature. Jets are streams of gas and dust expelled from internal nucleus cavities when solar heat contacts regions containing compacted volatile materials. In 3I Atlas, several observatories detected jets oriented in different directions, indicating the presence of multiple active zones on its surface. The intensity and direction of these jets varied as the object rotated, generating specific patterns in the coma and tail. These jets not only provide information about internal composition, but also about the physical structure of the nucleus, the orientation of its rotation axis, and how heat penetrates its internal layers. Another important aspect was the analysis of the speed at which material was expelled from the nucleus surface. Observations showed that smaller particles were accelerated more strongly by solar radiation, generating longer and thinner structures in the tail. On the other hand, larger particles such as microscopic fragments of dust and ice moved at lower speeds and formed denser and more visible sections. This behavior is coherent with physical laws governing the interaction between solar radiation and cometary particles and allowed astronomers to estimate the average size of material expelled during different activity periods. The shape of the tail also showed notable changes as the object moved away from the Sun. In the days following perihelion, the tail underwent a process of stretching and dispersion, mainly because materials released during the maximum activity phase began to move away in different directions depending on their size and charge. The tail became more elongated and less dense, reflecting the transition between the maximum activity stage and the gradual decrease phase. Despite this, the comet maintained a moderate level of activity for longer than usually observed in native comets due to delayed release of volatiles trapped in internal layers. The detection of an anti-coma at certain moments also allowed study of specific details about dust distribution. The anti-coma is not a second tail or a strange phenomenon, but a visual effect that occurs when heavier particles that the solar wind cannot push quickly remain grouped in a direction opposite to the usual angle. In the case of 3I Atlas, the anti-coma became temporarily visible due to the combination of orbital geometry, nucleus rotation, and the nature of expelled particles. This allowed more precise identification of dust grain size and how material dispersed around the nucleus. Images obtained before and after perihelion showed a clear evolution in the nucleus structure. Although no large fractures or signs of significant fragmentation were recorded, changes were observed in the visual texture of the nucleus due to surface material detachment. This is completely expected, since in their first encounter with solar heat, interstellar comets usually experience more intense surface erosion than comets that have already had multiple perihelia. 3I Atlas showed no signs of structural instability that could endanger its integrity, suggesting that its nucleus possesses adequate and sufficient internal cohesion to withstand this phase without disintegrating. One of the most important findings was the confirmation that the nucleus has a composition very rich in primitive volatile materials. As the comet's departure progressed, observatories detected that activity decreased but not immediately. Even weeks after perihelion, the coma showed considerable density, indicating that internal layers continued releasing material. This behavior matches theoretical models describing how interstellar objects can maintain prolonged activity due to their thermal isolation for millions of years. In addition, the object's rotation played an important role in how tail changes developed. Jets oriented in different directions caused small variations in comet motion, a phenomenon observed in other similar bodies. This interaction between volatile expulsion and rotation allowed study of how internal changes can influence external dynamics. In 3I Atlas, these effects were moderate and did not cause a dangerous increase in rotation speed that would have represented a fracture risk. On the contrary, the data indicate that the nucleus remained stable throughout this phase. The combined analysis of these changes allowed the conclusion that the internal structure of 3I Atlas is consistent with that of an interstellar comet formed in an extremely cold environment where chemical processes evolve slowly and where the most volatile compounds can remain intact for extremely long times. Each measurement, each image, and each recorded variation in the nucleus and tail helped build a complete portrait of how this interstellar visitor transforms when encountering an active planetary system like ours. The trajectory of 3I Atlas after perihelion became one of the most important elements for understanding its orbital behavior and for confirming again its interstellar nature. Once an object surpasses the point of closest approach to the Sun, its motion begins to follow a curve that clearly reveals whether or not it belongs to the solar system. In the case of 3I Atlas, orbital calculations showed from the beginning that its exit path continued to be hyperbolic, that is, an open route that does not retain it within any gravitational region of the Sun or planets. This means its visit is unique and that it will not return in a future cycle, definitively distinguishing it from long-period comets that are gravitationally bound to the system. Measurements taken in the days after perihelion confirmed that the object's speed remained higher than solar escape velocity, even after suffering the natural deceleration caused by solar attraction during the approach phase. A native solar system object would not maintain these conditions after perihelion. Its trajectory would adopt an elliptical or parabolic shape depending on its origin. The fact that 3I Atlas maintained an excess of speed even after its maximum approach mathematically confirms that its journey began far beyond solar reach and that no force within the system was responsible for accelerating it to this level. As it moved away from the Sun, observatories continued monitoring its position with great precision. This follow-up allowed refinement of orbital models that showed absolute coherence with an interstellar entry trajectory and an equally open exit. Each orbital parameter update matched previous predictions, demonstrating that the object did not experience strong gravitational perturbations during its passage. Although bodies like Jupiter can alter trajectories in some cases, the route of 3I Atlas passed too far from any giant planet to be relevantly influenced. The absence of significant perturbations also allowed confirmation that the object did not suffer large fragmentations that could alter its motion. In other comets, especially those with weakened internal structures, ruptures or massive detachments can cause detectable changes in trajectory. In 3I Atlas, analyses showed that its course remained stable, indicating that nucleus integrity was sufficient to withstand perihelion without affecting its orbital dynamics. This provides important information about its internal cohesion and how interstellar objects can behave in extreme thermal environments. Another key study area was the exact direction from which the object entered and toward which it is now heading. By analyzing its motion vector, astronomers were able to identify the approximate region of the sky from which it came, a relatively isolated zone in terms of stellar density. Although it is not possible to associate it with a specific star due to the enormous time it may have been traveling, it was determined that its origin does not correspond to typical trajectories of objects recently ejected from nearby planetary systems. This suggests that its interstellar journey may have lasted millions or even hundreds of millions of years before encountering the solar system. Dynamic models also showed that the object poses no collision risk with planets or minor bodies during its exit. Its trajectory leads it gradually away toward the outer solar system, losing itself again in the region where the Sun no longer has dominant influence. Although its passage provided extremely valuable data, the confirmation that it will not return and will not interact with any internal body facilitates prediction of its future motion without constant adjustments. The object's light curve after perihelion also provided information about its trajectory. As the comet moved away from the Sun, its brightness began to decrease gradually, something expected as activity reduces. This decrease follows a pattern compatible with reduction in sublimation rate and progressive nucleus cooling. Photometric measurements confirmed that this brightness drop was not irregular but followed a predictable and stable behavior. This reinforces the idea that the object's activity is driven by natural thermal processes and not by events significantly altering its mass. In addition, orbital studies performed with combined data from different observatories showed that the trajectory of 3I Atlas follows a geometry that will take it away toward deep interstellar space without its path crossing the main plane of the solar system again. This route is consistent with initial parameters measured since its discovery and demonstrates that there were no additional forces unexpectedly altering its motion. Each calculation reaffirms that its entry and exit follow the expected dynamic patterns for an interstellar body only temporarily deviated by solar gravity. Simulation models also allowed study of how comet activity may have minimally influenced its trajectory. When a comet releases very intense jets, these can create small thrust forces that modify its orbit. In 3I Atlas, observed jets did not have sufficient intensity to appreciably alter its trajectory. This is because although the jets were clear, the nucleus size provides enough mass for these thrusts to be insignificant on such a large orbital scale. This confirms that the object's dynamics were dominated exclusively by normal gravitational and thermal forces during its solar system passage. The exit of 3I Atlas also allowed study of how dust released near perihelion disperses. As the object moved toward colder regions, particles in its tail began to separate more clearly, facilitating modeling of their trajectory. These particles also follow routes influenced by solar radiation, allowing estimation of release speed and grain size. The observed distribution matched comet activity models for objects with high initial sublimation rates. All this helped build a complete picture not only of the nucleus, but also of how expelled material interacts with its environment. Finally, the complete post-perihelion trajectory analysis confirmed that 3I Atlas continues moving away from the solar system, following a stable and coherent route with celestial dynamics principles. Nothing in its motion suggests unexplained phenomena or behaviors incompatible with current science. Its farewell to the solar system represents the end of a brief but extraordinarily useful visit for modern astronomy. The visit of 3I Atlas to the solar system not only allowed detailed study of an interstellar comet, but also opened a direct window to processes and environments that exist beyond our star in regions of the galaxy inaccessible to any human instrument. Every interstellar object that passes, even briefly, brings with it chemical and physical information stored for millions or even billions of years. These fragments are relics of the environment where they formed, vestiges of planetary systems that may have existed long before the Sun itself. 3I Atlas was no exception. In fact, Its behavior, composition, and activity helped reinforce what modern astronomy has begun to understand about interstellar space. One of the most important elements revealed by 3I Atlas is the confirmation that interstellar comets can contain significant amounts of volatile compounds that remain intact during long periods without a nearby heat source. This indicates that the environment where the object formed was extremely cold, probably at great distances from its original star. In protoplanetary disks, the outer regions are places where dust, ice, and gases accumulate under very stable conditions. The presence of these compounds in 3I Atlas suggests that the object could have formed in a system with characteristics similar to the outer regions of our own solar system, but subjected to a completely different history. The study of interstellar comets also allows understanding of how planetary systems interact with their surroundings. When a system experiences gravitational instabilities, especially during its early formation stages, it can expel objects toward interstellar space. These fragments end up traveling the galaxy without fixed direction, influenced only by the forces of stars they encounter along the way. 3I Atlas, like 1I/Oumuamua and 2I Borisov, is a clear example of this process. Its passage demonstrates that material expulsion is a relatively common phenomenon in planetary system dynamics, helping confirm theoretical models of planetary evolution that predict the existence of millions of wandering objects among the stars. Another essential aspect shown by 3I Atlas is the chemical variety present in objects that did not form around the Sun. Obtained spectra revealed compound proportions that do not completely match those of native solar system comets, although they remain coherent with known physics and chemistry. This not only confirms that there are differences in planetary formation processes in different galactic regions, but also allows scientists to directly compare materials from remote environments. Each detected element helps build a chemical map of the galaxy, offering clues about how molecular clouds, planetary formation disks, and young stellar systems evolve. The activity observed before and after perihelion revealed additional details about the comet's internal structure. The fact that the nucleus maintained its integrity despite intense heating indicates that its internal cohesion is greater than expected for an interstellar object. This suggests that compaction and aggregation processes in the system where it formed were able to generate durable structures. In other words, objects expelled into interstellar space can be more resistant than previously assumed, opening new questions about how cometary nuclei form in different stellar environments. Brightness and activity variations also provided important data on the interaction of interstellar material with solar radiation. The behavior of 3I Atlas followed expected patterns for a comet exposed for the first time to a heat source. Intense volatile release, coma changes, jet presence, and tail evolution confirmed that physical models developed for studying local comets can also apply to interstellar comets, though with the differences typical of objects that have never been near a star. This validates many theories that predicted how these visitors would behave if they reached our solar system. Another important contribution of 3I Atlas concerns validation of galactic dynamics models explaining how interstellar objects travel through the Milky Way. The comet's trajectory matches predictions about how a fragment ejected from a distant system can move among stars without being gravitationally bound to any of them for millions of years. Its entry and exit from the solar system show that these objects can cross stellar regions without significant alterations, indicating that space between stars is more stable than some older models suggested. These data help improve simulations studying the motion of small objects across the galaxy. 3I Atlas also allowed comparison of interstellar comet activity with that of 2I Borisov, the only other precisely studied interstellar comet. Although both showed volatile-rich composition, the thermal behavior of 3I Atlas had notable differences, especially after perihelion. This suggests that interstellar objects can have very different thermal histories depending on the time spent in deep space and the environment where they originally formed. These comparisons allow scientists to develop a more precise classification of interstellar visitors based on their activity, composition, and internal structure. Finally, the visit of 3I Atlas revealed something fundamental. Interstellar space is not empty. It is full of fragments, molecules, dust grains, and remnants of ancient planetary systems that silently travel between stars. Every time one of these objects enters the solar system, it brings a time capsule, a set of preserved materials that tell the story of their origin. 3I Atlas offered another confirmation that the Milky Way is a dynamic ecosystem where planetary systems are not isolated entities, but parts of a complex network of material exchange across space and time. What no one told you about what is happening with 3I Atlas becomes completely clear when looking at the full set of data obtained during its passage through the solar system. Each measurement, each image, and each spectroscopic analysis revealed a coherent picture. It is an interstellar visitor that preserves within it a chemical and physical history older than the Sun itself. Its behavior not only matched what modern scientific models predict, but also provided unprecedented details that allow better understanding of processes occurring in remote galactic spaces. In this final part, the intention is not to repeat information, but to integrate what this object truly meant for contemporary astronomy. 3I Atlas demonstrated that interstellar objects are not rare anomalies, but real components of the galactic ecosystem. Its passage confirms that planetary systems do not form and evolve in isolation, but also expel material into deep space. This comet is tangible evidence of that process. Its primitive composition indicates that it originated in an extremely cold and distant region from the star that gave it birth. That means there are environments in the galaxy where volatile compounds can be preserved for periods that easily exceed the age of the solar system. This fact alone already represents an important change in our understanding of interstellar chemistry. The recorded activity also provided information on how these objects react when encountering a star for the first time. Intense sublimation, jets, coma expansion, and complex tail structures demonstrated that solar heating acts as a revealer of its internal composition. Instead of catastrophically eroding the nucleus, heat allowed deeply buried materials to surface within hours or days. These processes are key to understanding how interstellar comets behave when crossing star-inhabited regions and confirm that physical models developed for studying local comets can be successfully applied to these visitors. Orbital analysis was another of the fundamental pieces for understanding what happens with 3I Atlas. Its hyperbolic trajectory left no room for doubt. The object does not belong to the solar system and will not return. Its passage is unique and finite. This information allows more precise study of how wandering comets move among stars. By analyzing its entry direction and the inclination with which it crossed the solar system plane, astronomers confirmed that it came from an isolated region, probably without recent close interaction with stars. This suggests that the object may have traveled for millions or even hundreds of millions of years before encountering the Sun. In astronomical terms, this makes 3I Atlas a messenger from an ancient time, a fragment that formed when galactic conditions were different from current ones. Perihelion observations provided the most concentrated set of data. The comet's behavior under extreme heat reinforced the idea that its nucleus possessed a compact and resistant structure. No major fractures or signs of structural collapse were found. This indicates that formation processes in its system of origin were sufficiently stable and efficient to produce a body resistant to thermal stress. These details help refine models of planetesimal formation in cold regions of protoplanetary disks and demonstrate that interstellar materials can be preserved in very good condition even after millions of years. In addition, observations made after perihelion showed that activity did not disappear immediately, coinciding with the presence of volatile compounds buried in deep nucleus layers. This behavior confirms that heat slowly penetrated the object's interior and released materials that had remained isolated for long periods. This pattern matches what was observed in other interstellar visitors such as 2I Borisov and reinforces the idea that these objects share common characteristics regardless of their exact origin. The role of the James Webb Space Telescope was essential for reconstructing the object's chemistry. Its spectra confirmed the presence of compounds indicating an extremely cold environment in its region of origin. The Webb allowed analysis of how these compounds emitted infrared radiation as they were released, providing essential data for understanding the heating and sublimation process. No other instrument in orbit had the ability to detect hidden molecules inside the object with such precision. Thanks to these observations, scientists obtained the clearest evidence so far of the molecular structure of an active interstellar comet. For their part, Hubble images helped capture the visual evolution of the object with sharpness impossible from Earth. These images showed dust dispersion, coma expansion, and formation of fine structures in the tail. All this allowed analysis of how solar radiation interacted with released material, helping improve dynamic behavior models of cometary particles. Ground-based observations complemented this work by capturing brightness variations and rapid changes in activity, creating a continuous record of the object's behavior. 3I Atlas also showed the importance of international collaboration in modern astronomy. Its passage was observed by multiple telescopes on different continents and by several space instruments. This coordination allowed construction of an extremely detailed dataset, covering all comet phases from initial approach to solar system exit. This type of joint effort has become indispensable for studying objects that pass quickly and will never return. What no one told you with enough clarity is that 3I Atlas was not just another astronomical event, but a direct confirmation that the galaxy is full of fragments of worlds we will never know. Each interstellar object is a missing piece of a planetary system that no longer exists or that could be so distant that its star is not even visible from Earth. 3I Atlas thus becomes a chemical capsule, a silent witness to an environment that formed in a remote epoch of the galaxy. Its passage demonstrates that the Milky Way is a dynamic space where planetary systems evolve, collide, reorganize, and continuously expel material. The deepest meaning of its visit is that it provides physical proof that we are not isolated in a static corner of the universe. We are immersed in a constant flow of interstellar material that travels freely between stars. Every time an object like 3I Atlas crosses our system, it reminds us that we are part of an active and ever-changing galactic network.